Our entire world revolves around the Earth orbiting the Sun, which then orbits a black hole. The smallest change in direction or axis rotation can have a dramatic effect on the orbit, so obtaining accurate measurements from cosmic objects are very important. This lab calculates the net force components from observing the motion of a star orbiting a black hole to determine the mass of the black hole. The results with the corresponding net force and its components listed along with the black hole having a mass of 1.31 times 10 to the 34th kilograms. For Newton's second law, the net force can be broken down into parallel and perpendicular components. When taking the derivative of this formula, you get this updated one. The instantaneous rates of change of momentum can be split up into parallel and perpendicular components as well. The parallel component will always be in line with the present momentum, which is represented by the change in magnitude of the momentum times the direction of p hat. This indicates that d by dt parallel will always and only correspond to motion that is speeding up or slowing down. The perpendicular component will always make a 90-degree angle with the present momentum, which is represented by the change in direction or p hat of the momentum times the magnitude. This indicates that d by dt perpendicular will always and only correspond to motion that is changing direction. Change of momentum is directly proportional to force, as indicated by Newton's second law. So when you add the parallel and perpendicular components, it is equal to d by dt, and therefore equal to the net force. When you add F net times time to the present momentum, the new momentum can be determined. A random list of values was generated using my email address, and this is the original data that was given. In the GlowScript code, these given data points are indicated in purple. In the while loop, the x component velocity is being calculated from taking the difference of the two corresponding data points and dividing them by the change in time between them, as the velocity formula equals the change in position over change in time. The same thing is done for the velocity in the y component. Then the gravitational constant of 6.7 times 10 to the negative 11 newtons meters squared per kilogram squared was plugged in, as well as the star's mass of 2.0 times 10 to the 30th kilograms, and the time interval between data points, which was indicated to be 1 day. In the next while loop, which ran until there were no more observed data points, the initial and final velocities were defined from those points. Then the initial and final momentums were calculated from the definition of momentum, mass times the respective velocity. The change in the star's velocity and momentum followed the formula of final minus initial respective values. dv/dt was indicated as in the fundamental principle, say the change in momentum or the change in time, which was also set equal to the net force as determined by Newton's second law. From the fundamental principles, it was determined that in order to find dv/dt, the change in magnitude per time as well as direction needs to be calculated. A hat was set equal to the norm of the final momentum, and the change in magnitude of momentum per unit time is written out to be magnitude of final momentum minus magnitude of initial momentum divided by delta t. Multiply these two values together, and the parallel component of dv/dt can be calculated. To calculate the perpendicular component of dp/dt, the formula of the parallel plus perpendicular equals the total dp/dt can be rearranged to be solved for just the perpendicular force. Because of Newton's second law, the change of momentums can be set equal to the corresponding force components. In order to calculate the mass of the black hole, the gravitational law can be rewritten to be solved for mass. So when you run the code, the net force is calculated to be 8.72 times 10 to the 28th newtons, with the parallel component equal to 1.42 times 10 to the 28th newtons, and the perpendicular component equal to 8.59 times 10 to the 28th newtons. In order to calculate the mass of the black hole, the average of all the other values printed was taken, and it equaled 1.31 times 10 to the 34th kilograms. According to Newton's second law, change of momentum for change in time is directly proportional to the net force, so the two are equal to each other as indicated in depth throughout this lab. It can particularly be seen when in the code the net force components are set directly equal to change of momentum components. If the star of motion stayed the same, but the mass of the black hole had changed, you would not be able to determine the new mass, as the original mass was calculated from finding the net force from the motion observed. If the motion stayed the same, there would be no difference in the net force, and therefore no change in mass.